Aren't you like that whenever any AI thing comes up, you'd say no? Okay, all right. Okay, so this we talked about this last time. This is the start of the notes. By the way, the next homework, which is posted, is on the next 4 lectures and these notes, basically, as well as the book, the book reference, like the homework that's not due gives you the references in the textbook. Good book. Okay, so just to review, because I think I didn't actually write a definition last time, but um, a continuous random variable is any random variable that has associated with it this function called a PDF or a density f, and that is a positive function and integrates to 1. And in order to know the probability that that random variable is in some set B, you just integrate over B over here. Okay, so that's the way this works. As you see, it's different from discrete because X can be an uncountable number of possible values in general. It could be any number, say in the reals, but even if it's over some subset of the reals, any interval has an uncountable number of values, so you can't use a mass function. It won't work, even if it's some kind of a mass function that's decaying, like for the Poisson random variable or something like that, it still won't work. So you need to go to this other idea of a density. Okay, so here's an example. I don't remember this the same example as last time. It might be. Just made an example. So note here too that this is important. A lot of these are piecewise defined because typically part of the real numbers are just out of the picture. Think about the real world. A lot of times you don't want to model everything, so you narrow your focus to what is realistic. It makes the model more accurate usually, and usually better mathematically too. So this is what the density looks like. It's increasing and goes from 0 to 2. So I won't ask as many questions or look at you this way, how I'm always asking you questions. It's harder to do online like this. On the other hand, it's much easier for me to focus on what I'm talking about. But so you have to speak up. I encourage you to speak up. So this number is, here's my first question is?
2.
Yeah, 2. Okay, very good. Yep. Okay, then we have, so moving right along, we want to roll through this part and then get to the iPad with the notes. So we're going to call this usually capital F. Sometimes my capital F's look like lowercase f's and vice versa, but capital F will be the cumulative distribution function. This is sometimes called the distribution function. The PDF is not really the distribution function, although they're kind of, one implies the other anyway. You can see that by the definition here. So it's kind of loose. But sometimes because of my F's, I prefer to just write the CDF like this, which is what it is. Okay, and then Okay, so for that example up there, if I want the CDF, I just want the probability X is less than 0. Well, of course, it can't be. There's no probability over here. Any integral I take over here is 0, so it's 0. But between 0 and 2, I have to integrate this function. Let's go back up here. I have to integrate this function. So, I expect everybody can do easy ones like this pretty quickly. So this is x cubed over 3 without the constant, then the 3's cancel, so you get x cubed over 8. Oh, I get my choice, huh? So it's x cubed over 8. And you see it looks like this. It looks different, right? It's what the function value gives me here is a probability. It's the probability that the random variable x is less than this number down here. So say that's 1.75 or something. If I want the probability x is less than 1.75, I can just look at this function, plug 1.75 in, I get this height here, and that's the probability. It really doesn't do anything new. but it is useful for a couple reasons that we'll see very soon. So, okay, just want to know that. By the way, this is really important, and I don't write very well on here because I don't use the pen, but what's the derivative of this with respect to x? If I say what's f prime? Here, yeah, it's good you're waiting. Just f prime is what? F prime. So look at f up here. Can I take this is a function of x, right? Not t. And the derivative of this? Okay, now you can answer. Yeah, let me do it with the typing is better. F prime, capital F prime. I can take the derivative of this side. It's just the integrand evaluated at that point x, right? So, and that's called, does anybody know? You math nerds? Anybody?
The fundamental theorem of calculus.
Yeah, right. That's called the fundamental theorem of calculus. So it just says, that's what it says. You have a function like this where the variable is the upper bound here, and a dummy variable is used in the integrand. Of course, you can't use the variable here and here. Then the derivative of that function is the integrand evaluated at x. It's called the fundamental theorem of calculus. It's toward the end of Calculus 1 in any university calculus book. You can look it up. You can look up the proof. We're going to use it a lot. But just in this normal way, sort of, so to go back and forth between the CDF and the PDF. All right, very good. Let's keep rolling because this is still a considered somewhat review. Let's roll a little, and it's all good. Different medium, different style. Okay, f of x. Here's just another example. F of x is f of x is e to the minus x. So here I have something. Again, it's not defined on the real. It's but it has an infinite infinite size of values x can take on. X is unbounded, in other words. But you got a decaying density. Again, you still need the density idea. You can't use the mass, but in this case, it's decaying, and it works out the integral of that is 1. See the antiderivative of this? You could do it yourself, right? The antiderivative is minus e to the minus x. Evaluated at infinity would give you minus 0. And then evaluated at 0 would give you 1. So minus a minus 1 is 1. So you get 1. And here is the actual, if I just integrate it, if I do this and make the upper bound little x, well, first of all, I don't bother with the integral for less than 0 because that has to be 0. All those integrals are 0 over there. But then for any x, like if I put an arbitrary x in here and I want to know the probability I'm less than x, well, it's just the height of this. So it's just this value here, right? But that's just equal to the area under the curve, right? From x to 0, wherever this x is here. And it's just this area. I wouldn't want to shade it in, but you get the idea, right? I'm not going to worry about making a nice little shading picture here. So it's this area, right? So that area is this height here. By the way, if you watch these or you're watching it now and you're starting to fall asleep, understand one thing to do is to make this an active experience, pause it a lot, write your notes down, pause it, make sure you understand everything. You can't pause me in real time. You can pause the video. All right, so another example is this is a uniform. It's not uniform 0, 1. Now I just pick some arbitrary thing. Maybe it's the days of the month or something. And we're saying it could happen anytime between the 13th and the 20th. And we want to model it that way. So it's an even probability that some event could happen anytime between the 13th and the 20th of October, say midnight to midnight. And so it might have this density here like this. So what's the probability it's less than 13? 0. What's the probability it's greater than 20? 1. And in here, again, you just want these integrals. So say the probability it's less than 15 should just be this area, 2/7, and etc. And you can take the antiderivative of a constant if you like, you get a line, and you get this line here. Okay, so you put in 15, you get 2/7. You put in 20, you get 1. I mentioned this last time, maybe it's helping now. To see this again, if you take the antiderivative of the density, the result will be continuous, although not necessarily differentiable every point. It's going to be differential over the parts where it's smooth, but where you have, obviously you have jumps in the PDF is not continuous. Where you have jumps, then you will have still smoothness in the CDF, but you get non-differentiability. Okay. Now, example 2 and 3, example 1 is almost a famous type, but I made it from 0 to 2. So it's really something a little different. It's like a scaled beta distribution, but it's not really immediately recognizable with parameters usually. But example 2 and 3 are the very common ones. 2 is called exponential with rate 1, and 3 is uniform, and you just give the endpoints with the uniform one. All right. So soon I'll go to the iPad and write some notes. We're not going to have too long of a class today, got about 45 minutes left. Well, I want to go a little further for one reason. When I started looking at this, I thought some of this stuff you could do on your own. I mean, it's really just calculus. I don't need to come up here and do derivatives for you. I'm over it. Yeah, and then some of it too is really not so helpful to write notes on the board. It's better to see the big picture and to see pictures. So we're going to do a little of that more, take the class a little further down into here, and then we'll shift over. Any questions so far? Is there a new chat? Okay, I'll read the chats after. So, okay, so look, we have a new one now, okay? And this is the PDF. So all you need to define X is a PDF. All right, so we have a new one, and this is called normal, and actually it's usually lowercase in here. This can be lower, upper, doesn't really matter. And you have 2 parameters now. Remember, for the exponential, you get a rate, maybe you remember from 2 weeks ago or whatever. And for the uniform, you have 2, right? You have the 2 endpoints. Here you have 2 also. These are just parameters. You can make up your own continuous random variables and put however many parameters you want. 13, it's up to you. Okay, so this is the density for it. And yeah, Tamid?
Sorry if I'm jumping ahead, but
No, it's okay.
the sigma, is that outside the square root or inside the square root?
Is it what?
The sigma, the standard deviation, like
Yeah,
in the
so we write, yeah, right. Yeah, very good. Sigma, if I take the square root of this, or if I write this as like 3 squared, then 3 is the standard deviation, and he is jumping ahead, but that's okay. So probably dispelling some misconceptions because this, well, they're not misconceptions. It's true. This is the expected value of X and this is the variance of X. But what I'm trying to make clear is that you don't really need to say that at the start. They're defined as parameters, and then you will see that there are also those things. So for example, every random variable has an expected value and a variance. Well, it could be infinite maybe, but they're computable. But they're not necessarily have anything to do with the parameters. So just trying to separate those two ideas for you as you're starting your continuous random variable journey. Okay, so so here we are. So F is even symmetric about mu. Notice you can see this just by looking at this. You don't have to know its expected value or anything, right? If I go 1 unit greater than mu here, like say X is mu plus 1 or X is mu minus 1, I get the same value for the density. So I get a density function that is even symmetric about X equals mu. It also is maximum at X equals mu. Let's look at X equals mu. So this is stuff you don't want to write for the first time on the board. It's not necessary. So at X equals mu, this becomes 0. And you get 1 over square root of 2 pi sigma, whatever that sigma is. If it's a higher variance, what is the maximum value of F of X? It's lower. So you get something that's flatter and spread out more, okay? The lowest the variance, well, say super low variance, like something less than 1, like 0.01, you get something extremely peaked, right, at mu, and goes way up like this and down, and all this is still integrates to 1, but you see you get a very high value here. And then, so I'm trying to make a picture of a flat one and a peaked one, and it all has to do with, I'm going to show you some better pictures. Now I knew I wouldn't be able to draw this right. It all has to do with sigma and sigma squared, right? Not with mu. So wherever I'm at mu, this is what it looks like. If sigma is a big number, you get the low one, the flat one that's spread out. And if it's a small one, small variance means tight, a lot of knowledge, and you get the peaked one. So does anybody know, anybody who's done any statistics, what what 1 over, and I know you can look this up, so don't tell me if you look it up. I just want to know if you know. What's 1 over sigma squared called in any kind of statistics? In any kind of random variable? I mean, not only normal. 1 over sigma squared, 1 over the variance has a name. Okay, I know people may be checking, but so it's called the precision. So low variance, high precision, right? Low variance, I know a lot. High variance, low precision, 1 over. Okay, so precision, it's a real word. It's comes into use. Okay, F is even symmetric. It has a max at X equals mu. This is also called the mode. This will be part of our vocabulary. When we say the mode of a random variable, we mean its maximum density or maximum mass, even if you want to go back to the discrete ones. I know they used to teach us in grade school that the mode was a thing of a random number that could be the most, that happened the most. And so that's true if it's discrete. It's where the mass is the highest, but when it's a density, it's actually more useful. In fact, it's just the maximum point of the density. Okay, it has inflections here at 1 standard deviation. This you can show easily by just doing the second derivative. Okay, and you get inflection points there. Maybe I'll do this on the notepad, on the iPad. If it looks like it's something we want to do. Let's see, we got other big plans. Okay, so F cannot be analytically integrated except at 1 value, at mu. Okay, so I can say that the integral from minus infinity to mu or mu to positive infinity is 1/2. You might think that's strange because mu doesn't split the axis up evenly, but it's okay. These are limits, and both the limits, the numbers are getting so small that it works. Okay, so it's 1/2 to the right of mu, 1/2 to the left of mu. Okay, in R, you should use the command p norm of b to find the value. I mean, I was thinking actually earlier that I could show you by just doing a simple Riemann sum or trapezoidal method or something that this works, but I'm not going to do it. There's also a proof of this fact that this integrates to 1 in Ross. It's pretty nice proof. There's one step that's you cheat slightly on because it's more advanced, but basically he shows you that that it's true. Okay, so in other words, this integral here, and now I've just gone to mu is 0 and sigma squared is 1 for convenience. This will integrate to 1 from minus infinity to infinity, or it will integrate to 1/2 from 0 to infinity. Okay, and in R, this P norm B equals this integral. So it's the probability that a standard normal random variable, something that's normal, has the shape of a normal random variable with mu 0, sigma squared 1, is less than any real number B. You type this into R, P norm B, and it gives you this. And one of the big points about this lecture is to see how to go back and forth between standard normals and non-standard normals. This is a learning outcome for this lecture. But it's not terribly difficult or anything or involved, so we just want to see it. Okay, just make this picture here for the standard normal. And it's just a terrible picture, terrible artwork, but it's okay, right? It gives you the idea. You see what I'm after here. That's all I'm trying to do. A lot of times, well, okay, never mind. Okay, so here we go. Here's 1 over square root 2 pi right at 0. That makes sense. It is almost 2/5. And here's my little picture, completely symmetric. There's no reason I couldn't also pick other values. Maybe I'm interested in other things and I want to know these probabilities. Well, I could just use P norm B minus P norm A to get this area here, right? And that's the probability that X is in here between A and B. And what's one thing I know about this number? Just from this one picture. Go ahead. I'll give it to you. Go ahead, have fun, play with me. What's the probability Z is between A and B? What's one thing I could say? It's too easy for you, I know. It's less than that, right? It's less than 0.341. So I'm just saying, it gives you some, you know a little bit, some values here, gives you a starting point. And then you go to R, or there's also tables that you can use. Those are good too sometimes, or like sometimes it's a good way to give a test is rather you don't want people to use the computer. Maybe you're going to teach this. Give them a table with a bunch of values. They should be able to use a standard normal table even for non-standard normal random variables. So this is one of the goals today. It's an important goal. And here it is. Okay, so without further ado, we're at this fact here. Okay, I'm ready to shift over. I mean, maybe I'll try to cheat it and get the whole class in this way. I don't think this is going to work though. So, okay, so there's this relationship between any two normal random variables. In other words, if I have X is mu sigma squared, then I could take a linear function of X and get another normal random variable, and it will have this distribution, according to what A and B are, so you can manipulate them. In particular, you can go back and forth between standard normal and non-standard normal. This is the main tool that you will need, but it's true in general, and we were going to use it occasionally other times too. But okay, so notice that we get to Tamid's remark earlier that this is true. I say I'm being very careful here. I did not claim to prove this yet. It's in the notes. I don't think I'm going to do the whole proof today, but not long, but tedious, as I said, just calculus. But what I want to point out is that this fact here, that if I take a standard normal X, I multiply it by a number A and add a number B, these are numbers, I get another normal. And it says, actually, I guess you could say it says three things, but really it only says one thing. And it's the one at the bottom here to give it away a little bit. So it says, well, you get something normal. The mean is just transformed linearly, just as the random variable, right? So if I have X, multiply X by A, add B, the mean, do the same thing. Multiply by A and add B, and that's the new mean. And for the variance, well, there's no variance in adding a number, really. It just shifts everything. All the variance is in the A times X. It's all in the X, but when you hit it by the A, then it gets hit too. So you get A squared, sigma squared. And if we knew this was true, since if we did this first, which is the reason I didn't want to, then we would see nothing new. We would say, okay, yeah, the mean has to be that, and the variance has to be that, nothing new. Okay. But it says more than this. And the big thing it really says, and you might not see this because it's so early in our study of this. So a total understanding, if you didn't see this right away, is that Y is also normal. Okay, you don't always guarantee that. Like if I took an exponential random variable, or I took that first one with the something like 3/8 x squared from 0 to 2, and I multiply that by something and add something, you don't get something that has the same shape necessarily, or has the same distribution. So if I take an exponential lambda and say I multiply by 5, I don't get something that's exponential 5 lambda. But in this case, you get a normal back. It's one of the many, many, many amazing properties. Or maybe there's only one, and it's a result, it causes all the other amazing properties of the normal random variable. But there's something very deep going on with the normal, and thus its uses and all that too. So, all right, so we want to get this is a learning outcome. We want to understand this this transformation, and we'll prove it too. So first, though, a couple of useful cases. If I start with a standard and take a linear transformation of the standard, I get something normal that, notice the mean is just B, because originally the mean was 0. So I'm just shifting, everything was centered at 0. Just think of it as a shift. I'm shifting it to have a center of B. And originally the variance was 1, but I'm scaling it by A. So the new variance is A squared. The new standard deviation is A. Okay, the next one's even more important, I think, because it's how you use the software, it's how you use the tables. So if you have something that's already shifted out by mu and has a scale of sigma squared, well then, to make it standard normal so that I can use p-norm or tables. And of course, there are commands where you can just type the mean, and R has one too. You can type the mean and variance in. But it's still, trust me, it's still important to be able to just go back and forth between the standards. So then X minus mu over sigma is equal to this. I want to see more the A, B thing, acting on it a little more. So it's really 1 over sigma times X is the A, and then the B is minus mu over sigma. And right? Yeah, if X is this, then, and then I take AX plus B, then I'm really taking 1 over sigma times x plus minus this. So you could think, put your mu in here now for x to get your new mean, that's 0. And for your new variance, you just don't worry about this at all. And you just take, your new variance would be the variance of x times this number squared. So you get sigma squared over sigma squared. So you get 1. Okay, so that's the transformation that gets you back to normal 0, 1. So you can see you can go back and forth between these two, and then you can make the same picture as the standard normal, only now you're wherever you are. So if you want to think of this as a test, midterm or something, and mu is 70 or something, and say the standard deviation is 5, maybe 75. This doesn't look very realistic. You're going to go, that could happen. So maybe the standard deviation is bigger. It's like 15 or something. But anyway, you could see, you could still go back to that same picture and these same values of the 0.68, you're within 1 standard deviation, 0.95 about, you're within 2, etc. Okay, I don't want you to get bogged down by this. I want you to really see the big picture for this part. So, okay, so using these results for x normal mu sigma squared, yeah, so you could do things like this. Now, what's the probability x, the raw x is less than mu k plus sigma squared? So I could just look over here. Well, say k is positive. If k is positive, say k is 0, it's a half. Say k is 1. I'm sorry, mu plus k sigma. Say k is 1. It's just going to be, we know this is 0.5 over here already, so it's going to be 0.841, etc. And you, just to give you an idea, I'm saying there's probably not going to be integral values, but you have an idea of what's going on, the big picture. That's very important, so you don't get messed up when you're doing it. So, but look, let's now do the algebra out. So probability x is less than that. I'm going to just standardize it, and then I can use p norm. So I'm going to subtract mu and divide by sigma, and everything works out when I put it in this form like this. Normally, I might not have a nice form like this. I just have some number over here, but I can still do this and get a standard normal variable over here. So I'm just going to do the same thing to both sides. I have x here, this here. I'm going to subtract mu and then divide that difference by sigma. And what do I get? I get z over here, a standard normal. For some reason, we use z for this to alert you. Z, standard normal. Less than this, but this reduces, right? You see, you do things in the right order. Mu minus mu goes bye-bye. Sigma divided by sigma goes bye-bye, and you get k. And it's just p norm of k. All right. Now, I'm going to prove this on the notepad, and it's not too long, and then do some examples. Yeah. Before I do that, let's just do an R example and just to see how we might do this nice and slow. Okay, so say so we could just put some comments here. So is this the comment in R? I forget. Dollars, yeah. Yeah, so comment is a hashtag, right? Back to R. Yeah, so let's make a random variable. Let's say x is normal with mean. Let's do the example before, 70 or 80, say, and variance equals, let's make it a perfect square. Let's say 100. And so the standard deviation would be 10 then. Okay, now, so you got the idea. You don't have to think of this as a test. It could be anything. It could be like points per 100 possessions in the NBA or something like that, or whatever you like. So it's 80 and it has a standard deviation of 10. So let's take, let's find the probability. You tell me, what do you want to do? The probability, so probability X is less than, let's go a half a standard deviation, okay, 85. Now, what's one thing you can tell me about this? It's got to be,
Less than or equal to 0.341.
yeah, that's yeah, a half plus 0.341, right? Very good. So, right, remember the half too. So this is just saying it's less than, yep. Your center point is 80. And then between 80 and 90, you have 0.341 probability, right? And so, yeah, actually, if we think a little about this, we can get a bunch. So this is going to be, so we're going to say it's going to be greater than a half, because I know it's at least a half, because the probability that X is less than 80 is a half. And this is a bigger event, right? This is that's a subset of this event. So it's going to be a half plus, now it's not plus, quite plus 0.341, because that's all the way. But I could actually say a little more, right? Because I know the density is decreasing. So it's got to be more than half of 0.341, you know, so it's got to be like, I could say 0.17, for example. So it's got to be greater than this. This should give me an error if I type this. Yeah. So let's just get that number though. This is going to, well, we can do it in our heads, right? It's 0.5 plus 0.17. So it's 0.67. So I expect this number to be bigger than 0.67. Let's find it exactly. Now, two ways to do this is I could just, and I suggest this too, if you don't, you know, use the tool and all, but we can just use p-norm and type in the mean and variance. So it's p-norm. This is the CDF function. This is the probability X is less than this number. So p-norm of 85, comma, and then type mean equals 80 and variance equals, or standard deviation equals 10. You can do either one. I think if you do standard deviation, I think you can do partial completes and stuff like that. So you could just do, sorry, but now I got to fix it, right? Standard deviation is 10. Okay. And I get a number. Yep. Notice it's true. We knew it would be bigger than this, than 0.67. And we get this number. Okay. Now let's see to do it with the transformation. So in other words, if I take P norm of 85, P norm, okay, so P norm of 1, say, given mean equals 0 and SD equals 1, so standard normal, is going to be 0.841 or something like that, right? So it just lets you drop those arguments with the standard, because this is the most common one. And so it says this is just P norm. You just put one number in. You want to know what the probability of standard normal is less than 1. What happens if I put 85 in here? What do you think the answer is going to be? Yeah, it's 1, right? I mean, it's standard normal, a little less than 1, but not very much. So it's just going to give you all its precision and still say it's 1. Okay, but now how could I do what I want to do there and get that number 0.6914625 using a standard normal? Well, you do it like this. So we're going to write it, we'll write it out here. So probability X is less than 85 is equal to probability. Now, you can always do this, right? In math, you can do the same thing to both sides. I'm going to subtract the mean, which is 80. Remember, I use a kind of random typing algorithm, and then divide by the standard deviation. But since 10 is a positive number, and adding and subtracting maintains your inequality. Dividing doesn't necessarily, because it could be negative, but adding and subtracting does. So, but 10 is positive, so it maintains the inequality. So I have this is true. And now I just do the same thing to this side, but this is just 85 minus 80 divided by 10. And over here, I have the same thing. I have, so over here, I have 5 divided by 10, or 1/2. So this is just, as you see, and people already did this transformation in their head, I think. You can see that the question about whether this random variable, x with mean 80 and standard deviation 10, is less than 85 is exactly the same question as whether a standard normal random variable is less than 1/2. For that, you could say, well, it's got to be greater than 1/2 because it includes all the negative numbers, and then it's halfway through that first piece on the right side, and that's 0.341, so it's got to be at least 0.17. So we make the same conclusion, and you could say that what we really want, if we're going to do this over here, is just p norm of 1/2, right? So this should give me the same thing. You put 0.5 in, and it gives you the exact same number. In fact, for you coders out there, what do you think that this is doing? It's calling the same base function as this. And what do you think this is doing? It's just doing this simple little arithmetic first in some kind of macro style and calling the same base function here. All right. That's very good. Let's see. We've got 15 minutes left, 17 something. I don't want to go too long. I want to have a chance to talk to people, but I do have enough time to do that proof. I want to do it because I want you to see that and to see, that technique a little bit too. And then we'll just leave it there, and we'll continue with this next time. 2 full lectures to cover the normal. Sounds about right. And then we'll move on. But the next 4 are all on those notes. And the next homework, which is already posted, is all on those notes. So that's what we're going to do now. Okay, iPad gets to join. Oh. All right. All right. So I want to do some examples. I want to do the proof. Let's do the proof first. So proof. My writing might be off a little. All right. So what do we say? So I better write the thing down again. So we say let x be normal. Let's call it mu sigma squared. Then y equal ax plus b. Are you seeing the notepad? Is normal. Can somebody tell me? You're seeing it, right? Oh yeah, okay. All right. Well, I'm somebody will speak up. Okay, hold on, let me. Okay. All right. Okay, so how do we do this? Well, this is going to come up over and over again. So I want to, so the strategy is to find PDF of Y. and then just show it fits the definition, right? So the thing we gave above, the definition for the x is the PDF for standard, for a normal that we gave at the very start of this with the exponential and the 1 over square root 2 pi, all that. That is the definition of a normal random variable. Nobody else can take it. That's taken. That's the definition. So if I want to show y is normal, I have to show it has that PDF. And I'm going to do that. And I'm going to show when I do that, I'm going to show that these fall into the spots of the parameters where they're supposed to. In other words, where the mu was before, now I get a mu plus b, and where the sigma was before, I get, or the sigma squared, I get a squared sigma squared. Okay. But to do that, I can't go straight. You can't go PDF to PDF. So this is not going to work. It's actually an interesting mathematical idea, and it doesn't work. But so what I have to do, I have to take the PDF, go to the CDF, go to the other CDF, and then go back to the PDF. Can you think of anything like this in life? I can't. I'm honestly being just very, well, until now, I was being pretty sincere. But I can't, I mean, I could think that there must be things like this. Nothing comes to mind right away, but I know there's stuff like this where you got to like go into one world and do something, then you come back and you're, okay. So this is the strategy. So I'm going to try to find the PDF of y by first finding the CDF of y. And then how do I get the CDF once I have the PDF? What were the magic words? Differentiate, right? Fundamental theorem of calculus. So let's write this out again. So if I have p y less than little y, this is just a dummy variable to give me the function. This is equal to this integral. Now this is a lowercase f. I'm going to put a big Y here because now you got more than one RV floating around, and I don't want you to be confused. So this means the PDF of Y. Now, what variable should I put in here? Really anything you want. We'll just put little x in here because it kind of works nice. Okay, then this is the PDF of Y. So I want to show that this has the normal shape and must show. So show normal with these parameters up here. Okay, then how do I actually find this? So I compute this, I go down here somewhere, and then I take the derivative of this. What we said, the fundamental theorem of calculus, right? If I take the derivative of fy, little y, I'm sorry, this should be like x or some other letter, dx, then this is f little y of y. So this is my strategy. I'm going to start here, get an integral, and then differentiate the integral and see that it's normal, see that the parameters are right. All right, here we go now. Ready to go. All right, so it's in the notes too, and in Ross too, probably. Yeah, of course, it's in Ross too. Okay, so probability, let's see, probability y less than little y. Now, first step is do the thing we just did. Probability ax plus b is less than little y. All right, now, okay, now x is, right, x is mu. Did I say this up here? X is as this. All right, that's fine. I just want to, I know X though. I know its density. So I want to isolate X. So I go equals probability X less than or equal to little y minus b over a. And I'm just going to write over here, this is for a greater than 0, but it's similar for a less than 0. The inequality would flip and you'd have to deal with a -1 at one point, but you get the same result. Notice if a is 0, the question's kind of simplistic and we can basically ignore that, okay? Okay, so now I just have this, which I know what it is. I know the shape of everything, so I'm going to write it out as an integral. This is a little tedious, but this is the step you got to do. Remember, y is a dummy variable. It's not really a random variable. It's not really a variable even. It is a variable, but it's just a regular variable. So little y minus b over a is the upper bound. And now I just put in the density for capital X, 1 over square root 2 pi sigma. I'll write exp because this is getting a little bit bigger coming up. Okay, this is just writing the density for X in here. Okay, all right, very good. Now, fundamental theorem, right? So little f y of y is just the derivative of this. Okay, so this, I'll write one line to just remind you, dd little y, let's just write this, probability y. I always think it's kind of fun, writing derivatives in front of probabilities. But I could see why you might not think that right now. But anyway, this is what it is. So I take the derivative of this, and as you know, all this is this function evaluated at this upper bound here at little y. Maybe you don't know this. This is kind of the chain rule too, right? Because this is really like a u, and that's u of y. So I'm really doing the chain rule. I'm taking the derivative of f of g of y. And so the result is f prime g of y times g prime of y, right? Chain rule. Chain rule. Calc 1. Chain rule. So this is equal to, first step, let's do the first step first, even though I'm going to leave a little room for the other one because I want to put that over here. So 1 over square root 2 pi sigma in the denominator still. Everything, you just copy it down. exp, just copy it down. In here, you put g of y. Copy it all down. One really nice thing, though, the integral's gone, right? That ugly little dx over there is gone. And you just have a function now. You have a density. I'm not quite done, though, because remember, I got to do the g prime of y. What is g prime of y? What's the derivative of this function with respect to little y? Yes, just 1 over a, right? Linear function, just 1 over a. Okay, look, good things are happening. The a comes to sigma, the a comes to sigma. We're almost done. Let me just indulge me for one step so I can make it prettier. This is 1 over the square root 2 pi. Group the a and the sigma, just so it's easier to see. And then exp. This doesn't change. Clearly, I think it's clear. I want to get that a down in the denominator in one place. So let me combine everything in this top part here and bring the a beneath. So I'm going to get something up here squared. And in the bottom, I want 2 a squared sigma squared. Now, the a is already squared here, so I'm just taking it outside here. So really what I need to do is multiply and divide mu by a, and that would do it, right? So I get y minus b minus a mu. Okay, you're really done. I'll give it one more. Clean it up. Yep. Okay, another thing. So this is the proof. You're done. Fundamental theorem of calculus, the chain rule, the trick of using the CDF. That's all that's in this proof. Okay. All right. One other thing, this is defined. This is one of the few, well, not, there's others, but this is one, there's others. This is, for us, it's kind of new. This is defined for every real number, the normal, and any normal is defined for every real number. So it never doesn't make sense. It could not make sense, I guess, but it's never undefined. Okay, let's do one quick example of using this, and then more of this next time. This will really get used out Monday. It's 3:27. I'm just going to do this example and then wrap this up, and then we'll recap it next time. You don't want to go too long on these recordings anyway. So one example. So I think then more interesting examples next time. So example, let's just say X is normal. Mean 39. Say the variance is 16. So if you just write a number here, it means variance. Sometimes if you want to emphasize what you're doing, you could put like, write it like that and show that the standard deviation is 4. If you just write the number, it means variance. If you write SD equals, that works. But don't just write a number and expect people to think it's the variance. They'd be wrong to think that. Okay, so we want to know, find, very straightforward. Maybe I'll just do one of these, and then, so say find the probability X is less than 36, and then go to another one. So you do this the same way. So of course, one way is you do P norm, 36, comma, mean equals 39, SD equals 4. It will give you the number. But if you say you're using a standard normal table, you could do it like this. Probability X less than 36 equals probability X minus 39 over 4 is less than or equal to 36 minus 39 over 4. But this is normal 0, 1. So this is equal to P norm of this number. This is minus 0.75, right? Minus 3/4. Okay. It's less than a half. I don't know if I did it here in my notes. So I get, yeah, it's less than a half, and it's also less than whatever, 0.17. So it's less than 0.67 or something like that, right? Like for the same thinking that it's half of that interval. And it's or whatever the other, it's less than 1 minus 0.67. That's what I should say, I think. So it's less than 0.32 or something like that. So we get actually 0.227 is what it turns out to be. Yeah, because it's even 3/4 over. So it's not the midway point. Okay, anyway, you get the idea. So yeah, I don't want to do the next main thing. How about one more quick example? Let's just do quick example. Say, let's call this A, and let's say B. Say find the probability X is between, yeah, go ahead.
From where did we get this 0.227?
Say again?
From where did we get this 0.227?
Yeah, from R.
R, okay.
Yep, some good question. This is, gotta type this in. I notice the browser doesn't support this either, so maybe there's something else like standard normal CDF or something, but. So if I do this, again, you could do this on each side. You notice as you get more and more used to this, it's not that big a deal. You just got to be careful about the inequalities, but basically it's the same deal, right? So let's just do this a little quicker here. So 28 minus 39, I get minus 11. And then let's divide by 4. And I take X minus 39 over 4. This sometimes you could write is like this, write it just in line, save space. And then this is less than or equal to, what is it, 35? Yeah, 35 minus 39 is minus 1.
1.
Yeah, minus 4 over 4, so you get minus 1. So yeah, so you can see for a standard normal, it's the probability that, you know, so here's the inflection point, right? Minus 1. You come all the way over here. This is almost minus 3, but minus 2.75 or something like that. So this is this probability. And yeah, so how to do this in R? So I like just always using P norm and not messing with 1 minus P norm or anything. So I would just type in P norm of minus 1. That gives me all the area to the left of minus 1, and then minus P norm of minus 11 over 4 or whatever. And this will give me 2 numbers. Subtract them. You could do it all on one line like this, and it just gives me, I get 0.1557, something like that. Okay, so that's the probability that if we were the mean was 39, and I want to know, and it's definitely wider, 4 variance of 4, so, and I want to know the probability between. Does that seem too low? No. Oh, 35. Yeah, 35. So that's 35. Yeah. So you're already starting at the influx. Yeah, I didn't make the picture look right here. So okay, let me just go right back. Almost done. Almost done. So here we have the inflection somewhere. So it's just the inflection here at 35 minus 1, right? And all the way down here to 28. These will be the same thing. It's just calculus. It's the fundamental theorem of calculus, and the really is the substitution method in Calc 2 that's at play here. That's it. All right. I'm going to stop recording, and I'm staying on the meeting in case you want to make arrangements to meet or want to try to talk. It might be hard for privacy, but we can meet on Zoom today and tomorrow or in the office next week. So let me stop this first, though, and then take your calls. Stop recording.